All right, so Chapter 10. In Chapter 10, we are going to talk about the Internet. I love the commercial where the guy was sitting down to the computer, and after a few hours, he was done looking through the Internet. The Internet today is a basic tool that we do banking, learning, that we communicate with family, friends, employers. So it is fairly important that we look a little bit closer at how it works. And to connect today's discussion with last week, I want to talk right off the bat about a protocol that, just like other protocols, was developed because of a need, okay, and is added to a whole bunch of protocols we already talked about. The protocol I want to mention is MPLS, or multi-protocol label switching. Okay. Last week we talked about routers, how they will use protocols to connect between each other. But basically what they're trying to do is they're trying to pass your packet through the shortest route to the destination. But to do that, you see, they have to open the packet, investigate it, see the IP address where it's going, see the time to live in the IP protocol, and then move it along. And so it takes time to open up these packets, okay? Which means that these routers cannot really investigate every packet as far as figuring out, okay, is this a VoIP packet or is it a data packet? Maybe we should do something different with a voice over IP packet. So the need was created to speed up this routing process, and there was also a need to maybe limit some of the point-to-point infrastructure. So MPLS steps in, and MPLS, being a labeling technology, allows us to take a packet, put a label on it, and then move it across the internet just based on that label, without having to open it up and look inside. This does a couple of things to our traffic. Number one, makes it faster as the router passes packet to the other router, because they only look at the label, and things are moved along to the destination. Some things are copied into the MPLS protocol from IP, like time to live, the TTL flag. So how many hops can you do? Okay, we'll copy that right into MPLS so that it's readily available to the router that's going to pass the information forward. Okay. The second thing that happens is routers now would be able to, within the MPLS system, they can guarantee quality of service, because the label itself specifies that this is a voice over IP packet, and make sure that it gets there as soon as possible. Whereas data packets, they can wait, they can be queued, they can stay behind. So MPLS made it not as important for us to have dedicated lines. You see, if I wanted to have two offices connected and have VoIP over it, where we guarantee the connection bandwidth, you'd have to go the expensive route where you are leasing a line, you have some point-to-point protocol. Also, MPLS allows us to now do VPNs or tunneling over the internet, because with the label set correctly, see, it's going to have security set up around that label, and it can move across in a tunnel. So MPLS, you see, is an upgrade. We talked about ATM last week as sort of the best of the worlds, being a cell switch technology, very quick. Now MPLS allows us to use the same infrastructure as the regular internet does, but it allows us to put quality of service requirements. Therefore you can, as you're buying the service, you can expect that your voice over IP is going to be working really well, even though you're being routed through multiple places. So I want to start with this because sometimes this gets lost, and MPLS is definitely one of those technologies that right now is used quite a bit. So folks are even going away from ATM and frame relays. Next week when we talk about telephones, we will go back to frame relays and how some of this bandwidth can be protected. But MPLS is where it's at as far as creating quality of service. Okay, so let's talk about the internet and the history of it. Okay, does anybody know how the internet started? ARPANET. All right. And what was that all about?
Connecting different universities to collaborate.
Yeah, yeah. Universities were connecting. Yeah. I want to tell you that the creation of the internet has to do with Sputnik. All right, the Russian satellite. It also has to do with the missiles in Cuba. All right. So now what I want to do is I want to show you just a quick video animation that's going to explain that connection. Of course, some of you might have heard that the internet was created in China, or politicians got involved in that. Like they say, success has many fathers, and failure is an orphan. So let's take a look at some of the details of history of the internet here. All right, that's fine. Let's switch this to. All right, I'm going to switch it to 360. I think it's going to be good.
The internet. In the year 2009, we send emails, make calls over the internet, and discuss topics we take an interest in. Even our banking is going virtual. But what we take for granted today was only a vague idea 50 years ago. In order to understand how we got this far, let's go back to 1957, when everything began. Before 1957, computers only worked on one task at a time. This is called batch processing. Of course, this was quite ineffective. With computers getting bigger and bigger, they had to be stored in special cooled rooms. But then, the developers couldn't work directly on the computers anymore. Specialists had to be called in to connect them. Programming at that time meant a lot of manual work, and the indirect connection to the computers led to a lot of bugs, wasting time and fraying the developers' nerves. The year 1957 marked a big change. A remote connection had to be installed so that the developers could work directly on the computers. At the same time, the idea of time-sharing came up. This is the first concept in computer technology, to share the processing power of one computer with multiple users. On October the 4th in 1957, during the Cold War, the first unmanned satellite, Sputnik 1, was sent into orbit by the Soviet Union. The fear of a missile gap emerged. In order to secure America's leading technology, the U.S. founded the Defense Advanced Research Project Agency in February 1958. At that time, knowledge was only transferred by people. The DARPA planned a large-scale computer network in order to accelerate knowledge transfer and avoid the doubling up of already existing research. This network would become the ARPANET. Furthermore, 3 other concepts were to be developed, which are fundamental for the history of the internet. The concept of a military network by the RAND Corporation in America. The commercial network of the National Physical Laboratory in England. And the scientific network, Cyclades, in France. The scientific, military, and commercial approaches of these concepts are the foundations for our modern internet. Let's begin with the ARPANET, the most familiar of these networks. Its development began in 1966. Universities were generally quite cautious about sharing their computers. Therefore, small computers were put in front of the mainframe. This computer, the interface message processor, took over control of the network activities, while the mainframe was only in charge of the initialization of programs and data files. At the same time, the IMP also served as interface for the mainframe. Since only the IMPs were interconnected in a network, this was also called IMP subnet. For the first connections between the computers, the Network Working Group developed the Network Control Protocol. Later on, the NCP was replaced by the more efficient Transmission Control Protocol. The specific feature of the TCP is the verification of the file transfer. let's take a short detour to England. Since the NPL network was designed on a commercial basis, a lot of users and file transfer were expected. In order to avoid congestion of the lines, the sent files were divided into smaller packets, which were put together again at the receiver. Packet switching was born. In 1962, American Ferret aircraft discovered middle and long-range missiles in Cuba, which were able to reach the United States. This stoked fear of an atomic conflict. At that time, information systems had a centralized network architecture. To avoid a breakdown during an attack, a decentralized network architecture had to be developed, which, in case of loss of a node, would still be operative. Communication still used to work through radio waves. That would have caused problems in case of an atomic attack. The ionosphere would be affected and the long-wave radio waves wouldn't work anymore. Therefore, they had to use direct waves, which, however, don't have a long range. A better solution was the model of a distributed network. Thus, long distances could be covered with a minimum of interference. Another milestone followed with the development of the French network Cyclades. Since Cyclades had a far smaller budget than ARPANET, and thus also fewer nodes, the focus was laid on the communication with other networks. In this way, the term Internet was born. Moreover, Cyclades' concept went further than ARPA's and the NPLs. During communication between sender and receiver, the computers were not to intervene anymore, but simply serve as a transfer node. Cyclades' protocol went through all machines using a physical layer that was implemented into the hardware, providing a direct connection with the receiver and end-to-end structure. Inspired by the Cyclades network and driven by the incompatibility between the networks, their connection gained in importance everywhere. The phone companies developed the X.25 protocol, which enabled communication through their servers, in exchange for a monthly basic charge, of course. DARPA's transmission control protocol was to connect the computers through gateways. And the International Organization for Standardization designed the OSI reference model. The innovation of OSI was the attempt to standardize the network from its ends, and the channel's division into separate layers. Finally, the TCP assimilated the preferences of the OSI reference model and gave way to the TCP/IP protocol, a standard which guaranteed compatibility between networks, and finally merged them, creating the Internet. By February the 28th, 1990, the ARPANET hardware was removed, but the Internet was up and running.
All right, so this little historical view really shows how it's the political winds that oftentimes drive technology in places, because oftentimes you do need the support, right? The strategic direction and support of governments and large organizations. So a few protocols were mentioned during this presentation. Specifically TCP/IP as the one that really empowers the Internet. And by now we also know that there are a whole lot of different protocols as well. So we've talked a lot about TCP/IP, but let's walk through some of the other protocols. Okay, who remembers what DHCP does? Go ahead.
Sorry, it generates an address and a dynamic address.
Yes. Okay. So DHCP is going to be a dynamic host configuration protocol, and it allows us to assign out of a pool of addresses your temporary address. Now this is very useful, not because we have a shortage of addresses. Okay. This was developed because we don't want to have to go to every computer and assign an IP address, especially in labs or on the floor of an organization. Imagine taking your laptop to McDonald's, and the first thing you have to do is stop by or ask the receptionist or the employee to come in and type in the IP address for you, right? That would be counterproductive. So that's what DHCP does. It's going to give you automatically an address. What else does DHCP deliver in addition to just the IP address? What are the other numbers that you need in order to get online? So ports, port would be, let me explain ports in just a minute, but ports are something that is assigned at the system level, at the operating system level. But I'll go to ports in just a minute, yeah. What did you say? Subnet mask, yeah. In fact, there's a picture here, right? DHCP, we're going to have an IP pool of addresses. There's a subnet mask. If I was to look at my own system and say IP config, the numbers which are given to me by DHCP, well, first of all, I have the IPv4 address, okay? Then I have the subnet mask, which you mentioned. Then it's going to say default gateway. And this address right here, this address is the address of the router. So if I have packets that do not go to our local network, but they go to the internet, it's going to be channeled through the default gateway. And then there's yet another number that DNS servers would give us. I'm sorry, the DHCP servers. So the next number is right here, the DNS servers. So these three, the primary, secondary, and tertiary, are DNS servers. If one doesn't respond, I can connect to another one, right? But those are the required addresses for you to go online on an IP network. And so that's what DHCP provides. Just imagine having to copy those down and write them in or even track those. So DHCP servers do that very well. Okay, so that's DHCP. Okay, how about next one? How about the UDP? What does UDP do? All right, so book reading is overrated, huh? We actually talked about UDP some time ago. UDP, but it goes along. Let's see. Ooh, look how many different things. Here's our protocol. Basically, it goes along with IP, and then you have a choice at the transport layer, either for TCP or UDP. Whereas TCP is the resilient protocol, it helps IP, which IP is best effort. It's not resilient by nature. With TCP, IP becomes resilient. With UDP, it again is a best effort architecture. So when we do streaming, or maybe when we use something like syslog, we're just going to throw out those packets and not wait for any confirmation that they were delivered. So that's UDP. All right, let's take another one. How about the ARP? ARP. Does anybody remember what the ARP protocol does? It's a table, yep. Okay. Address resolution protocol, which applies at the local area network. So it doesn't have to do with routers, it has to do with switches, so that when your workstation, having a MAC address, connects to a switch, it has an IP address as well. So now the switch is going to track which MAC address is assigned, or which MAC address is assigned what IP address. And that's the ARP table. So that next time when you ask, I want to go to this IP address, it knows which MAC it is and which port to send you through. Okay, so that's ARP. And by the way, we've walked through some of these previously. Today they sort of pile on us because so many are actually listed. in the textbook, but they've appeared here and there through our discussions. So that's Address Resolution Protocol. How about NAT, N-A-T? Does anybody remember what that's for?
Address translation.
Excellent. And why would you ever want to use that?
Well, like the multicast stuff, or is it, basically you have one IP that allows any UDP network to operate over it?
That's exactly it. So, so consider your home setup where you have a modem, and that modem has the real routable, world routable IP address, but your laptops that you connect wirelessly get a local address like 192.168.1 and something for the host part. So you can have as many of these local addresses. But now when you connect to Google, see, you're going to go through this real routable address, and that's what we call NAT. This is a NATed address. It's local. In a way, it's a natural firewall. Okay? It protects those non-routable addresses from attacks and direct connections. And it allows us to have many different workstations behind one single real IP address. So that's NAT. Very good. Now, how about next one? Let's see the ICMP. Does anybody remember what the ICMP did? You know, all these protocols are like tools, right, in the toolbox. It's like the internet is like this broken car all the time, and you have to use all these tools to make it go. So what does the ICMP help us with? ICMP, okay, it's used with ping, it's used with traceroute, and basically, let's see, ICMP helps us to track the connectivity to routers. It also helps us to get feedback. When the packet is dropped, we will know what happened. Okay, so ICMP helps us to provide additional information about our traffic, something that IP by itself does not provide. All right, and then the last one here on the list in the textbook is VPN. Virtual private network, excellent. And why would you ever want to use VPN? Security, all right, security. So you were at home and maybe working for a bank, and you have to download a spreadsheet that has some sensitive information, right? As we know, as that spreadsheet travels over the IP networks, it's going to be handled by many different routers. And perhaps your neighbor is stealing your wireless and is actually able to sniff that traffic altogether. So one way to protect is to have a program installed on your computer, and when you double click on it, there you go, you have a device for that as well. Sure, so that's a two-token authentication. All right, so you press the button and you get a number, and that's from Cisco, which allows you then to authenticate into a VPN tunnel. So now your office, your organization is going to give you a new IP address, and the new IP address is protected through encryption through a point-to-point protocol between your workstation and your organization. And even if you use Telnet or if you use FTP, it's protected because it's tunneled through the different routers that we're connecting to. All right, so nice walk through some of those protocols. It's good to know at least as you read through the book, just make sure that at least they sort of ring a bell. All right, not that you have to memorize them all, perhaps, but those will repeat here in the future as well. So let's take a look briefly, and today I'm going to show you three videos total. One we already saw. The second one here is a little bit shorter. Now that we're talking about different protocols, there's this conference called DEF CON, and basically they talk about different protocols and what you can do with them. And I want to show just a little bit about IP. and NTCP. So we'll just watch that for a second. We'll start it there somewhere in the minute
Hello,
16.
everyone. Say hello, everyone. It is great to be here at DEF CON 19. Thank you all for being here. If you don't know me, hi, I'm Dan Kaminsky, and I write code.
All right.
So, of course, we lied through our tape. You know what's called IP spoofing. You just pretend to be some IP that the system trusts. You might say, but I thought networks blocked spoofing. It's like, yeah, it blocks spoofing from, like, your cable modem. I'm on the core of the internet. It does not give a crap what IP address I claim. The one thing that does care about IP spoofing, though, I have finally found something that the cloud does not do well. If you are running in a virtual node and you want to spoof packets, good luck. You can't do it. The hypervisor will stop you. You'd have to, I don't know, like have a hypervisor exploit. No one has those. Is IP spoofing still effective to do interesting things? Well, there's a DNS trick that I've been sitting on for a couple of years. You know, in DNS, you go to a server, you say, hey, go look up this domain. The server goes and runs around the internet, looks for the domain. You say, oh, hey, go look up a domain I control, and I'm, this random IP. You're not going to get the reply with the answer, but that server has to go run around the internet to go satisfy the request. And it'll run around to you. So you now see, oh, okay, my spoof type request spawns another request that comes back to me through another channel. Now this only works for obscure applications like DNS and UDP. Certainly nothing built on TCP, right? Well, limits of IP spoofing. Most modern protocols run over TCP. It's a reliable communication protocol. And TCP has sequence numbers. They're kind of like passwords that are exchanged in the beginning of a session to make sure that each side is really able to hear the other side. And it's rather effective, and it means when you don't get the reply because you spoofed your address, you're not able to get to the point at TCP where data is really going to be exchanged. Now, sequence numbers didn't used to be random, which meant people could just guess them out of thin air. Okay, so let's go ahead and make them random. Well, you can't just go ahead and make them random. See, the problem is that sequence numbers did not start out as passwords. They started out as markers where inside a session here's a bunch of bytes. Are they on page 1, or are they on page 100, or are they on page 500? You gotta know where to put the words. So the deal is, let's say you have a connection from 24123 on port 50,000 and 4221 on port 53. You gotta make sure if there are two connections and all that stuff is recycled, that random packets from the old session don't show up in the new session. It'd be like you're reading a book and suddenly a page from some other book shows up. It'd be rather confusing. The game is to have random sequence numbers unless the ID is the same. Then we go sequential. And that's done with a hashing function where you hash all the data with the secrets, you get some absolute number, and you add time. So if you have a slight difference in 2345 to 2346, the numbers become much different. But if it's absolutely identical, it becomes sequential with time. That is a problem. Where someone just floods us with connection requests. They don't have to remember all the passwords. They just need to flood us with requests, and we need to remember their passwords. So we run out of resources. This SYN floods over in dirt.
All right.
The solution came from Dan Bernstein. It's called SYN Cookies.
All right, I'm going to stop it right here. What I want you to hear is how easy it seems, IP spoofing or flooding, with SYN packets. As we talk about theory of IP, you can't do that. And yet, these guys, they figure out ways to do that. And to, most firewalls, you say you cannot get in unless you're from this IP address. And no problem, they can spoof that. They use flooding, and flooding it can be done even with ping requests. And yet flooding has an appropriate use as well. When a router comes online, it's going to flood its neighbors with that information. So I like some of these DEF CON shows, not that you want to register and put your name actually on the attendees list, but you can go back to YouTube and actually watch some of the recordings, because it gives you sort of a different view of the technologies that we sort of take as reliable, set in stone, and working well. All right, so this is just another view at the internet. So at this point, let's talk about those port numbers. So port numbers were mentioned also in this DEVCON presentation. So let's start with the idea of a NIC. Does anybody remember what NIC stands for? Yeah, network interface card. It's that green little card with the RJ45 connector, and so you plug in your network wire to it. Okay, single network interface card can have multiple interfaces on it. Multiple interfaces, it means that you can have multiple IP addresses on a single card. So let's say I have an ETH0, I might have ETH1, ETH2. These are different interfaces, and each can have an IP address. So now, with my ETH0, let's say that I have here an IP address of 192.168.1.100. All right. On that single IP address, I now can have multiple ports. I can go between 1 and some 65,000. Every application that is using networking on this IP address is going to have to reserve a port. That port then is related to a socket, which is a file that, let's say, my browser will write to, and then the network subsystem is going to pick up this data and send out through the network. So ports are like windows in a skyscraper. Okay? What it means is that some of them are open, some of them are closed, and the firewall will do that for us. The firewall will say, on this particular interface, on this IP address, you can only talk to port 80. Port 80 happens to be the web server port, and therefore if you try to use SSH or try to use FTP, it will reject any of these messages. On workstations, most often, if this is the workstation is going to connect to port 80 on the server. A web browser is going to ask for port 80 communication, but on the workstation, the port is going to be chosen randomly. So you may be communicating on 30,000 port and exchange information with port 80 on the other system. Okay, so the different ports are basically used for specific application. So there are standard ports assigned to standard applications. Service ports, and so here is maybe a list of them. See which page renders first. All right. There's some heavy lifting being done on this other tab. Okay, so port numbers. Here's the port, whether this is TCP or UDP, and then the description. So if we go to maybe port 80, being right here, hey, this is for HTTP, the Hypertext Protocol, or otherwise the World Wide Web. Maybe we go to a different port. Let's go to port 22, which is defaulted to the secure shell. Or maybe 23 for Telnet, or 21 for FTP. These ports have to be standardized because as a workstation, I need to know which port to ask for from the server. Okay, which is why, okay, this leads us to the idea of a URL, or a Universal Resource Locator. Specifically, here's a URL. The first field in the URL is this right here, and that's the protocol, right? I could switch this and I could say FTP. Okay, I could switch that and maybe call HTTPS. So that is the protocol. Then we have :// oops, and then this right here is the host name, just the host itself. Later we have the domain. Altogether, this is a fully qualified domain name, FQDN, a fully qualified domain name. Right after the fully qualified domain name, there's a field that's often hidden in the browser, and that's where the port goes. So if I press enter, okay, it connects on port 80 to the web server, and then the browser is nice, keeping it clean, and it hides the port. But maybe you have seen URLs before that have strange numbers after the colon. Well, that's where you specifically ask for a port number. Some administrators choose to use custom ports. Any idea why they would choose to do that? Why would you want to use a custom port and not a default port? Yeah, so a lot of times hackers will build systems, as the Kaminsky from DEF CON mentions. You can scan the whole internet and just figure out port numbers. So what they will do is they will scan IP addresses, and the list of IP addresses is limited. So you can have a computer scan the whole internet if you really want to. And then I will choose to scan port 80 just to see who's running a web server. And if I'm looking for a specific web server, maybe I'm looking for IIS version 5 because I have a hack for it, right? I can scan it, and if you're running on port 80, you're easy to find. But if you're running on some other obscured port, this is security through obscurity here, then I will not scan you as easily, and it'll be harder for me to figure out where the traffic is at. Okay, so that's the port number. Then we have directory. Now this directory can be virtual or it can be a physical directory on the server. And then finally we have name of the page or name of the resource itself. It can be index.html, it can be index.php or some other page. Often, yes.
Is there any significance for the two forward slashes after the first page?
I am not aware of a special meaning of these two slashes, other than that is basically the definition of in URL. So let's look at URL, and let's see. See right here, this is defined as a required element, perhaps to show the difference between the protocol and the start of the actual host name. No, I don't know, but if you find out where it came from, that'd be great. I mean, it is used extensively today, for multiple syntax. Right. No, so it's yes.
I assigned my camera to the IP address to the router, and then I assigned port 8050.
Okay.
Picked it out or whatever. Does that mean it's open all the time? And obviously you need a password to get in there. But
Okay, so camera, did you say?
yeah. So wireless camera.
Oh, got it. Okay, yeah, I was thinking, for some reason I was thinking pictures. Okay, so you have a video camera sitting somewhere. You assigned an address to it, which is probably a local NAT address, NAT, Network Address Translation.
Correct.
Okay, and when you are on a laptop within the same network, you can hit that IP, hit that port, and you get prompted with a password.
Right, and I can do the same thing from here.
Okay,
You have
so...
to put the colon 8050 behind it.
Okay, right. So if you do it from here, that means that you actually configured your router to either put this IP address in DMZ, so you basically put it outside of the firewall, or you did some tunneling where you did port forward, and you're saying whenever someone is sitting the real IP on the router on port 85, whatever it is, so you forwarded the port right into the camera. That means that anybody could scan it possibly and find it. The chances of someone actually scanning all your ports and picking that port, so you chose it out of the air, or was it in the instructions?
No, I kind of chose it.
Okay, that's better, because if it's in the instructions, then someone is scanning for it, right? So it doesn't have to be terribly bad. You could possibly look at your router and the firewall module there and see if it allows you also to specify maybe a subnet or a set of subnets where you would be allowed to connect from. So then you could specify, for example, the GRCC address as one and your work address. That way, if someone is scanning from China, they would not necessarily have access to it.
Yeah, I use that end service to set it up with, but I have a problem with that, so sometimes I just have to put the IP address in. Then I sign one to the router too. The IP address from the router, and then I put a port on that one also, so I can remote
Right.
the router.
But regardless, I mean, I think back to your original question, we still have to track your password.
Yeah, no, that's what I'm saying, that you still, can you get in there without the password?
No, so you can't get into the password. But is it HTTPS that's running on the camera, or is it HTTP that's running on the camera?
HTTP probably.
Okay, so then you got to be careful, because that means that when you submit your password, someone could easily see it. Yeah.
Right, I see what you mean,
Yeah. Also, if you are thinking about including that URL maybe on a web page somewhere or in your emailing to someone that URL, it will be out there in the open. And there are services, that basic services, more like bots, that go through and will harvest these URLs for scanning purposes. Yeah. But in general, you should be okay. There are additional things you could do. For example, you could set up an Apache reverse proxy, and on that reverse proxy you could set up through basic authentication, username and password, and then you have to log in first to the proxy, and then only it would ask again for a password of your camera. Yeah. Now, so anyway, anytime you expose a service to the internet, it's problematic. Perhaps a better way to do that would have been to do this. Allow remote administration of your firewall. Enable this port forwarding rule while you're using the camera remotely. Then disable it and log off. That way you can always log in to the router and then enable the external rule. But when you're done, disable it. That's right. Yeah, so it would take you just a minute to re-enable it remotely, but that way it's not available for scanning all the time.
It's not a real big deal, you're not going to look at it.
Yeah, well, you never know.
Keep the cover on it.
Yeah, exactly. Keep the cover on. Yeah. So, but especially if it's not SSL, I would definitely recommend that you not have it enabled all the time. Yeah, because even if someone catches your password, you see they will not be able to use it unless you enabled the service. Because likely your router is SSL. I'm guessing at it, but most routers probably would use SSL today. Yes, please.
You were talking about how it's like really unlikely that they'll scan it, choose the correct port to get to it. I think you just send requests there, and when you get a request for a password back,
Yes.
there's a port there that's active.
That's correct. But you have to go through all 65,000 ports on just a single IP. So let's just say that it takes a while longer than when you actually know of a port. So imagine cars in the parking lot. One has a open door, and then another one maybe has a protection on the steering wheel. Okay, chances of a thief stealing the one with more protection first are small. So most hackers will go for the lowest protected, low-hanging fruit first. And so that's why they look for a specific port, because they know that maybe this email package is on this port. Let's find that email package. Out of the millions of systems, they are going to find a few that they will be able to hack. And versus sort of long-range operation for actually finding the port, the specific port, and on every IP address, that'd be very, very time-consuming. Yeah. Okay. So the last thing I want to talk about is the later part of a URL. Let's see what would be the best example here. Somewhere here, I think I still have Blackboard open. And if I was to right-click on maybe our announcements. Okay, can you see at the bottom of the screen as I am hovering? At the bottom of the screen it says something like list content editable.jsp question mark. And then it provides content ID equals, then and course ID equals. These are parameters that you can pass to a web page, and then that web page takes those parameters as user submitted data to make some decision on it. So for example, what we're asking this content editable page to do is to bring out a specific course ID and to bring out specific item. And so then the back-end processing accesses the database and then displays the appropriate page. So that's how you pass parameters. The question mark is a key symbol that says, okay, now I'll be passing parameters. So when you fill out a contact form, here's your first name, last name, and email. The page will put together a URL that says question mark, first name equals John, and last name equals Smith, and email equals whatever the email is. Okay, so that's a URL. So let's talk about web pages in general, and really the fact of how can we create websites. What are some of the technologies that the browser uses during rendering of a page? Style sheets. Okay, yeah, style sheets. Let's see. So style sheets. What else? Any other basic technology that it would use in addition to style sheets? HTML. All right. So HTML. Here is how we can write HTML. We'll say maybe in bold, "Hello world," and we'll say this is my first page. So this is plain HTML, and I can go to save it on the desktop and call it mypage.html. And so I'm making sure that .txt isn't added to the end of it. Save. Now I can go ahead and find my page, which is right here, and I can say open it with a browser. And there it is, my page. Perfect. That's HTML. Let's add style sheets to it. So style sheet is a technology that allows us to make things pretty, but beyond pretty, it helps us to make things consistent and looking consistently. I can add a style sheet at a tag level for inline style sheets. So I could say, hey, style for this is going to be color green. And so now I added a style sheet which turns hello world green. Now I can have style sheets at the line level or at the page level so that all bold tags in this page will be green automatically. I can even extract my style sheet and put it somewhere on the server so that multiple pages or multiple websites can have the same look. And when I decide for hello world to be red, I do it in one place and all the pages would have that. That's the cascading part of the style sheets. Okay, what other technologies can we use in the browser? JavaScript. Okay, JavaScript. So JavaScript is part of what our textbook calls dynamic HTML. The idea of dynamic HTML was coined really for Internet Explorer, where they had to VB script. It was DHTML was a huge deal. Well, the scripting language that still survives till today is, of course, JavaScript, and it is the default one. So I can just say script, and now I can say something like alert. This is JavaScript, which, by the way, was developed by Netscape, and it survived the browser wars and actually made on top of those. So save that, and now I have a pop-up from JavaScript. Okay, notice that all of this is coming from the desktop. No servers involved at all, right? So All these technologies like HTML, JavaScript, CSS, they are being executed in the browser. Okay. Any other ones? Any other technologies that we can run in the browser? You can embed videos, yes. And you can do that with Flash. How does Netflix do it?
Netflix does, I think they use, yeah,
Silverlight, yeah. So they're using Silverlight. Both of these require a plugin to be installed. And then there's a special object tag that you put in HTML. And you download a binary file that basically is then rendered in the browser through the plugin. Okay, how about ActiveX controls? That's an Internet Explorer technology, but also it can be executed right in the browser. Okay, or Java applets. If you have Java runtime environment connected to the browser, you can run those local programs in the browser as well. Any other technologies that you have seen inside of? Okay, great. So HTML5 is a newer version of HTML. Whoops. Okay, here's HTML. Let's see. They probably are talking about it somewhere here. Okay, so HTML5 is a newer version of HTML, and it adds specific tags. Let's see if we can get a short list. There it is. Here's a video tag, audio tag. Let's see. Let's see if we can get a nice list of that. I don't think that's that one. Let's try this. Tags HTML5. It should give us some new tags. There we go. So here are tags, and then ones that are marked new or updated. And the more important ones, like the video tag, really is what is going to revolutionize the web, because today if you want to have video, you got to turn towards a proprietary technology. It can be ActiveX, it could be Flash, it could be something else, like Silverlight. But really, this video tag, which is going to be part of the standardized HTML, is going to allow us to have video players that do not require Flash, that will run on the iPad and other of these devices which previously had difficulty with the proper proprietary plugins. So yeah, so that's HTML5. Very good. Any other technologies that we can put on the browser? All right, if we look at this page, notice the XML extension. If I actually look at this page, okay, it's built through a set of tags. There's an opening record tag and a closing record tag. Opening name tag, closing name tag. XML is a language that is self-describing. Okay, oftentimes it is used to send data from one server to another. Imagine that you're sending a list of new customers to another office, and they're going to do something special with that list, send them flowers, for example. Okay, instead of sending a text file, tab delimited or comma delimited, where you put first name, then last name, then address, that can be difficult, because what if you do not have the last name value, or what if you switch the values back and forth? So this self-describing file would say first name, put the first name in, close it. Last name, put the last name in, and then close it. So a parser can then pick up and process this XML file without having extensive internal knowledge of what is expected, what should come, and where the errors could exist. Okay, but XML is also sometimes used to render the page. XHTML is just another version of or view of HTML, where some of the opening and closing tags are more rigorously applied. Okay, so this page of ours Okay, it works, and it represents browser technologies. But this is really Web 1.0, okay, browser technologies. I master and basically create a beautiful page, then I FTP to the server and everybody can read it. Okay. What we expect today is a little bit more. We expect to have a two-way conversation. I want to log into Facebook and I want to chat with someone. I want to submit data, and when I log in, I want to have everything customized to myself. And that is accomplished by server-side processing. Okay? So not only do we use the browser technologies, but we also connect server technologies like PHP, like Perl, like Java server pages, so that when you submit a form, I can grab this data and the parameters after the question mark. I can do something with those parameters. I can verify that maybe you're on Amazon. Okay, oh, you came back. Let me show you the products that we've gotten since you've been here. And I can draw it from the database, display to you. What comes back to the browser are still the simple text-based technologies like JavaScript, like HTML. But we put them together on the fly. They don't exist anywhere typed in and stored. We put it together on the fly, which is all great and enables e-commerce. But one major technology had to be developed for this to happen. And that is HTTP had to be somehow fixed from being stateless. HTTP is stateless in the way that when the browser makes a request to the server has no idea when the browser will make the next request. The server has no idea what IP address the next request will come from. The server has no way of identifying that browser. Oftentimes, we are behind a single IP because of NAT. So multiple workstations, multiple browsers are going to have the same IP address. Okay, so there was a need to somehow identify a browser even if the IP changes or even if multiple IPs, multiple workstations are behind the same IP. Does anybody know what this technology is that was developed? Has to do with food. Cookies, that's right, cookies. And Netscape came up, just like Netscape created JavaScript, they also came up with cookies. And cookies are basically files that the browser is allowed to save on the operating system or keep in memory. And today, cookies are not used to store your name or your credit card. Okay, that's not what cookies are used for. Cookies are stored to store a session ID. Okay, how many people have been to Culver's? Like a drive-through Culver's? All right, how many people have been to Arts and Bevs? Okay, a few too. Okay, so you go to buy your food, you pay, and what do you get back at Culver's drive-through or at, you get a number, yeah, a blue tag or a red one from Arts and Bevs. If someone was really smart, right, they could take the same number and go pick up your food, right? That's the whole idea with cookies, that once the transaction is done, you are logging to Amazon, you put in your username and password, you are now having the cookie that is remembered on the other end as logged in and who you are. If someone else shows up with the same cookie, they can buy whatever they want on your credit card. This is where cross-site scripting comes along. Because with cross-site scripting, I can write a little JavaScript, put it in a comments field, submit it to Amazon.com if they are not sterilizing the data. And then when you are looking at a page, JavaScript kicks in and it can send your cookies to an external website, and that will include your session ID. Therefore, now I can take that session ID and be logged into Amazon.com. Okay, that's cross-site scripting. So those session ID cookies. Now let's see what they look like. So we're going to go to Amazon.com, and to view your cookies on any browser, you just go ahead and issue JavaScript document.cookie. And here are my cookies for this website. And here's my session ID, right? This session ID will not change after I log in. But after I log in on the server side, it has a greater meaning because now it's attached to my account. All right. Can you change cookies on your browser? Can you modify them? I'm sure there's a DEF CON session on it somewhere. But here's how you would do that. You go to add-ons, and you look for an add-on called Cookie Manager, and there are many different ones. And then you go to Tools, Cookie Manager, and then you say, okay, I want to edit the session ID token, and edit it, right? And so now if I know what your string for that session ID is, I just plug it in here, hit OK, refresh the Amazon.com website, and I'm logged in. All right? So that's easy enough. All right. So we talked about cookies. We talked about some of the server-side systems. By the way, when you look at our Blackboard system, notice the .jsp extension. That stands for Java Server Pages. It means that on the back end, we use Tomcat and Java to recognize your username and password, to show you your grades, to process your quizzes. Other server-side technologies are available as well. Let's take a look at another one, directory. We're going to look for, okay, here is a page with .php extension. So the server-side processing language, which picked data from the database and displayed it back to us, is PHP. What other extensions have you seen on websites? Okay, so HTML or HTM mean that this is a flat, a static page, and someone basically coded it in. A lot of times the initial page you look at, it would be an HTML page. Although it is possible to configure your web server to process any HTML page as a PHP page or as a Java server page. How about Microsoft.com? What do you think they are using? Server-side processing from Microsoft. All right. ASP, right? ASP. So ASPX is the .NET newer version of it. So if I do view source on this site, I can see that, hey, they're using HTML, which is great. They're using JavaScript. By the way, they also use style sheets, and it's an external style sheet. Yeah, and that works just fine for them. But this page right here, see, not necessarily someone came and edited this in Notepad or some text editor, saved it and submitted. This likely is a database-driven page, and all this code is put together on the fly and then sent to you. So if you are an application server developer, you are thinking not just in terms of the interface that you're building, but you're thinking about how to produce this language to be submitted to the browser, and at the same time you have to imagine what it's going to look like when it arrives on the browser, right? So this would be the output of your programs, this HTML or JavaScript or cascading styling sheets. Very exciting work. All right, so that's what these extensions are all about. Excellent. Okay, so let's stop right here, and I want to show you one more video here. This one comes from a Google conference about the internet, and this one we want to go to about minute, was it 1.5, 1:50, okay. And in this picture, we see the fiber optics wires that go between continents. Remember last week we looked at, maybe it was 2 weeks ago, we looked at a cable being spread under Atlantic? Well, that's what they're doing today. They're actually putting these cables under really most of the oceans. Let's listen for just a moment what they're saying about this.
Slide here is a map showing the current undersea cables around the world. They're scaled by the capacity, how much is equipped and currently active in the system. So you can see between the U.S. and Europe, about 12 to 13 high capacity systems in place. Across the Pacific, about 8. Several South America and intra-Asian area. We're between Singapore and Japan, all with very high capacity. This is changing quite rapidly, actually, the way this map looks. Next year, you're going to see new cables to Greenland, to East Africa, even some of the islands in the South Pacific. So you're really seeing an expansion of the cable infrastructure in very far-flung places.
All right, so you can see that today growing the internet and the speeds of it is still based on these ships laying cable and growing this infrastructure. But let's move forward in this presentation and yeah, let's look at this view here.
So two questions. What is the relative cost of terrestrial versus subsea cables? And the other is, are you seeing any change due to the economic changes with global economic conditions in this segment?
In terms of the cost, it's going to vary by the region, obviously, and how much capacity installed, so it's really hard for the state differences. I mean, a cable going across Russia, the cost of that's far more expensive to maintain and operate than one going across the United States, for instance. The price is probably 10 times as high across Russia than going across the United States. The question about the impact of the current economic crisis on existing cable projects and cable builds. So far, we've not seen any projects being canceled at all. Cables are still being built. I think there's a youth project coming along. It's a hard time getting funded, but just in the past 3 months, we've seen 3 projects announced. Some big projects that have announced and contracts signed. So these are long-term investments that are being made. So there's a cable announced that goes up the coast of West Africa. It's going to be going into service in 2011. It's a $600 million cable.
All right, so there's great investments taking place, but notice how most of the traffic still goes through the U.S. Some of the main services like Google and Facebook are based in the U.S., and so that's where majority of the traffic passes through. Let's look through one more presentation here. And Akamai is the company. It's a networking company which is sponsoring some of this research taking place.
Base points in the internet. So we'll start with some packet loss and latency. And the data I'm going to show you here is at 2 nines. That means it's sampling at the worst 1% of performance. And the idea here is that, well, basically, if you take averages, things look pretty good. You know, modular getting into China, but otherwise, things are pretty good. And people like to think of their applications running in a data center at 5 nines. And the internet is far from that, and to sort of get a feel for that, this data is at 2 nines, so the 99th percentile of performance. And it's sort of what you'd expect. You know, if you're going in the United States, you know, things aren't so bad. So if you're going from San Francisco to Chicago, you know, you can do 60 milliseconds. This is data taken across a 2-week interval in the internet. Nothing dramatic happened during that time. At 2 nines, you got 6% packet loss. And you don't really have anything that you would call, you know, hours of degraded performance. You know, things are pretty good. Now I'm going to show you data on internet. That's just, you know, doing a ping from between the pairs of points in the internet. Akamai has an overlay on top of the internet, and that will show you what is capable with the hardware that's there. Okay, now you get access to all the wires. Your packets follow paths determined by BGP and what the networks, you know, want the routes to be taken. And we have our servers in 900 networks. We can sort of control how we map our data through the internet. And this says the best you could hope to do, you know, at 2 nines is 51 milliseconds. So not a big difference within the U.S. This is round trip time, ping time. So say you go down to South America, and you start to see some differences. Packet loss, not bad. At 2 nines, you still have no packet loss, pretty good. But you can start to see that your latencies are a lot higher than what you might think of as optimal. going to South America. So you're paying 300 milliseconds versus maybe some kind of notion of optimum of 180. And of course, if you were to go into China, which is maybe one of the worst places to try to go, packet loss only at 16% is pretty nasty at 2 nines. You have a hard time doing 2 nines into China, but you see dramatic latencies there, very bad. And look at the hours of degraded performance. Basically, every workday in China during the whole workday, it's very poor behavior, performance going into China. Yeah, there's a couple of reasons. It's when traffic increases, and there's very poor connectivity between the major carriers, CNC and China Telecom. And of course, there's a great firewall, at the perimeter of the country, filtering traffic coming in. And as traffic goes up, it becomes less effective, and things get really slow. Yeah. 2-week period. Yeah, it's pretty bad. In fact, there's degraded and there's unusable. Unusable is a subjective measure, is close to 10 hours a day during the weekdays. We probably could. It's not the hours you want to use, probably.
All right, so if you want to see more of this presentation, it's going to be linked from the course. But basically, it shows that because of the infrastructure already in the U.S., we are in a great spot as far as connectivity goes. And other parts of the world, they deal with their own issues. But just like creation of the internet was connected to political, winds, so the performance of the internet often is as well. And so you have in China where there's hours and hours of unusable traffic that happens. Okay, well that brings us to our next part in our class, and that is we're going to split into smaller groups, and you'll be able to explore 4 topics: the history of the internet, internet protocols, internet services, then locating documents on the internet, and create wikis. Okay, the textbook talks about different services for the internet, like email, like the World Wide Web, tweets, which we've used throughout the semester, Facebook and others. Well, wikis are a great technology, one that I'm very excited about, especially for documentation. If you have a team of people, or even for yourself, if you think about how do I document things, or maybe how do I keep notes for my classes, wikis are great because you can interconnect them, you can quickly grow them without knowing HTML code and things like that, and you can create a very alive system that helps you to keep the data up to date. Easy to mention Wikipedia. Basically a bunch of guys who thought, hey, everybody knows this stuff, let them edit it. Today you still hear at schools how Wikipedia is bad, don't use it for research. But the bottom line is that it works, I think. In my opinion, a lot of the technical elements, technical pages are constructed well. And if you try to modify it and you make a mistake, quickly there are people that are found to correct that. So today you'll be able to create your own wikis. To create a wiki in the system, you click on the title of the assignment, and then there's a big page, a big button that says Create Wiki. When you create wiki, you will go ahead and put a title of it, and then whatever in the body, whatever you choose. Okay, and we will we'll go into the detail of that in just a minute. Let me pause the recording from here. Okay, so to work with a wiki, you simply say Create Wiki, and it creates a new page. You go ahead and give it the title of the page. Next, if some wikis already exist, you can go ahead and include them as links so that the pages get interconnected. Also, you can use mashups, like the YouTube mashup, where you perhaps are looking for a specific subject, like maybe TCP, IP, and select a video. The video gets embedded onto your page, and the wiki gets created. You can use other elements like the link, hyperlink button, put in the URL, hit submit, and a link is going to be created. Let's say I'm going to wikipedia.com. Okay, and so here now we have a hyperlink. And there are other buttons. Explore them all, see which ones will work for you, and then grow the wiki. The requirements for the assignment are posted, and you will be able to complete it online. This is a collaborative effort where you can edit the page and include the work of others right inside of your page. Thank you.